So, in the last few lectures where we covered eigenvector centrality and other kinds of centrality, you might have noticed that we discussed something called random walks on graph. We said that eigenvector centrality, the way you compute it, it mainly measures, it's very closely related in fact to a process called random walks on graph. So, in today's lecture we will see in more details what are random walks on graphs. And you already know one very important result related to random walks on graph, that is about PageRank, the algorithm PageRank, the power iteration method. You also know things like the random walks on graph converge, in the sense that, you know, if you continue multiplying the matrix, transition matrix to itself, ultimately it converges to a particular distribution, and this distribution is nothing but the eigenvector centrality or the first eigenvector components of each of the nodes. We will look into more details of what is random walk, what are the different parameters associated with random walks, and what are the other applications of random walks. For example, how can we kind of extend the idea of PageRank and so on. So, we start with a very simple definition of random walk. So, given a graph and a starting point, by starting point I mean a node, you have to select a neighbor of it at random and move to this neighbor. So, this is a very simple definition. So, if your graph is undirected, you start from any node and you can go to any of its neighbors. If it is a directed graph, then you start at any node, but you only go to a node where there is a forward edge. So, if you are at U and there is an edge from U to V, then you go to V, but if there is an edge from V to U, then you need not necessarily can go to V. So, once you go to this neighbor, you repeat the same process. Then you select another neighbor of the node where you recently moved to and continue moving. So, this is called random walk, a very simple process. You go from node to node, node to node, following the edges, and the whole thing you do is randomly. So, you randomly pick up a neighbor and go to it. That's it. That's why it's called a random walk. So, this sequence of nodes that you select by doing random walk, starting from a node say V0, you go to V1, V2, V3 and you continue it. This particular sequence is called a random walk on the graph. So, just what I said pictorially, it would be something like this. So, here is a directed graph with 3 nodes A, B and C. There is only one edge from A to B, and therefore, the probability of taking this edge is 1. What it means is, if during the random walk somehow you end up at this particular node A, you have no other option but to go to B, because there is only one node connected to it. There is only one edge from A which links it to B. So, naturally you within probability 1 end up in B. Similarly, you have nodes like C, which is the only node you can come from B and so on, but from C actually you can go to 2 different nodes. You could go to A or B. So, this is the graph. So, you all know that this is the corresponding adjacency matrix. So, this is corresponding to A, this is corresponding to B, this is corresponding to C and so on. Now, from this adjacency matrix A, you could compute the what is called the transition matrix. You could compute basically the probabilities. So, from A, since there is only one node, the probability of going to that particular node B is 1. However, from C you see there are 2 nodes you can go to, A and B. So, you divide it by 2. So, the probabilities are half and half. So, in general, what is the factor by which you divide a particular node, the entries of a particular row? The degree of that particular node. So, and since it is a directed graph, if you add the values of the adjacency matrix of a row, what you get is called out degree, how many nodes you can go to from this particular node. However, if you add the columns, what you get is the in degree, how many nodes point to that particular node we are looking at. So, this is the adjacency matrix and this is the transition matrix. So, what the random walk says is, suppose you start at node A, this was randomly chosen or given to you. So, at time t is equal to 0, you are at A. Now, where can you move to in the next step? The only possibility is B. So, at the first step that is time t is equal to 1. So, steps and time, this variable t actually calculates the number of steps, and we call it time, although it is steps because it is a discrete system. So, you go to this particular node which is B. So, this is the person who is doing this random walk, and he then now jumped to B. And then from B you have again only one choice, which is C. So, now this person has jumped to C, and the random walk at after step 2 is A, B and C. However, now when this person was at C, he has two choices. He could go to either A or to B. So, but you know, since there is this probability half of going to this and half to going to this particular node, what you could think is this person got divided into two halves, one half went to this and one half went to this. So, this is a probabilistic view, and if you look at one particular random walk, you would either get ABCA or you would get ABCB, each with equal probability, which is half, and in this way the random walk can continue. Now, the question is, why are random walks interesting? Why should we study them? So, in general, many natural systems, many data sets you look at has a natural graph structure. For example, the web or the social the communication networks between people, or the social networks and so on. So, there are many processes that happen in these natural systems which can actually be modeled as random walks. Let us see a few examples. So, if you are looking at web as your data, then think of a random surfer. So, the surfer starts at a page and goes to another page following links and so on. We already discussed this during the last lecture when we were discussing the PageRank algorithm. So, this process of random surfing is nothing but a random walk on the web graph. Think of internet. By internet I mean you have servers and routers, and from one particular server, when you try to reach a URL, it will connect you to another, and the particular request will hop through a route and it will come back to you, the page will come back to you. So, this process of routing is nothing but a random walk, although it may not be completely a random walk, it might be more informed. In fact, in all these cases, even when you search, you might not be really a random surfer, there might be a skewed probability distribution, that whether you go to node A or node B, depending on what you are looking for and so on. But a very simple model is of a random walk. Why I say simple is because here you have very little parameter. Once you have the graph, you do not need anything else. Then if you are aware of peer-to-peer networks and file sharing systems like Shareza, Kazaa and so on, they also use this concept of random walk for searching. So, when you search for a particular file, it might use random walk as one of the means. And in social networks, like in the friendship networks or web social networks, the flow of information is also like a random walk. You would randomly tell one or two of your friends, and they tell one or two of your friends, and in this way the information percolates. So, routing is a random walk because it is not always fixed that. So, suppose there is a server and it is connected to 20 other servers. It is not necessary that your request will go to only one of the specific servers. It can choose one of the 20 and then it goes to some other one. So, in this way it can, so when it decides which kind of network to send, which server to send the request to immediately, that can be decided on randomly, and it is often done to avoid congestion, for example.
But that you take an example of a web server where you have 20 servers and you can distribute the load.
Right.
But that will be at only a specific location, not routing as such.
No, the phenomenon of routing is not a random walk. I am saying in the context of internet, you could consider routing as a random walk. See, information percolation in general is not a random walk, because it could be a broadcast. For example, I am telling all of you some things and you are listening to me. So, this is not a random walk that I am doing, but it could also be a random walk in the case of social networks. If you just leave it free, you do not guide it the way the information flows. So, we have seen some of the examples already. Let us see some more interesting examples, because these are very these are something which you could immediately think of. There are examples which are not so immediate. So there are some classical examples of random walk. The concept of random walk came from actually those classical examples. One is Brownian motion in physics. So you know that the particles, say dust particles, when you see them in a beam of light, you can see them moving around. So this motion is a very good example of random walk. It's not a guided motion. They randomly go from one direction to another direction. And you know, a lot of properties of these Brownian motion can be related to properties of random walks on specific kind of graphs. Then think of electrical circuits. So do you remember Kirchhoff's laws? So Kirchhoff's laws are nothing but another view of random walk. So what happens here, the electrons or the current, if you want to say so, you are given a network of resistances. The resistances are some sort of, you could consider weights, and where there is an intersection, that point is kind of a node. And when you compute that the current I1 goes this direction, I2 goes this direction, and compute the voltage and so on. So basically what you are doing is this current is doing a random walk on the network. So this is another very interesting example, and there is a lot of theory of relating random walks to electrical circuits, which I will not go into because they are very involved, but if any one of you are interested, I will definitely give a reference at the end of this lecture. You can look at them. Then in physics there is also something called, there are things called Ising models. What happens in physics is, a very common kind of model of physics is that of state change, which we very frequently use. So suppose there are different states. The simplest example of state change is, you know, solid, liquid and gas are three states, and you could go to solid to liquid and liquid to gas and so on. But if you consider every molecule as a kind of unit, and then it has an energy level which is kind of a state associated with it, and then you could do, the molecules could either go to the higher energy level or the lower energy level. Since it's not a general graph, it's a very specific kind of graph. It could go to either one layer up or one layer down. So the graph would look like, suppose these are the states, so it could come to this state or this state. So this is a different molecule and it could come to this state and this state. So the whole system looks like a grid. These are called lattices. It could be in 3 dimension or in general n dimensions. So you could do random walks on lattices, and these are very commonly used for explaining properties like ferromagnetism and paramagnetism. You know that these properties are, when molecules get directed, their magnetic alignment gets in a particular way, gets in a particular direction, then you get ferromagnets or paramagnets. So these are very well explained by lattices and Ising models. And these are classical examples. Here are some more examples. So you know of shuffling, right? So those who play cards, you know how to shuffle a deck of cards. It's a very important, you know, before starting any game you do that. So shuffling or even permutations can be done using random walks. So could you guess how? So right. So every permutation, say I have only 4 cards, A, B, C and D. These are 4 cards, and I have, say, and so on. So by one shuffle, actually you could go to, from A, B, C, D, you could shuffle B and C and you could go to this particular node, and you could come back. So actually this is an undirected graph. If you could go from this node to this node by one shuffle, the same is true, the reverse. So it's an undirected graph. There are other nodes which, for example, from ACBD, you could come to ADBC by shuffling C and D and so on. So you could construct such a graph on the nodes where the nodes are different permutations, and any if swapping 2 cards give rise to the other permutation, you could link them. Then the whole process of shuffling is, you start from a particular configuration and you do a random walk and reach somewhere else. And you want to ensure that you don't end up in the same node, or you end up in a sufficiently distant node, sort of. So you just keep on shuffling, assuming that it will happen. Sorry. and usually it happens because your state space is very large. So, it will diverge and go somewhere, and which will be distinctly different from what you started with. Another very beautiful example is that of music. So, if you know a little bit of music, you know that a composition is kind of a series of, you know, notes. Just one second. Sorry. A composition is a sequence of notes. Now, this sequence is not a random sequence. You could imagine that how many notes you have, basic notes? Not 7, actually 12 if you also consider the flat notes, and there are different octaves. So, if you consider 3 octaves, there will be 36 notes, but let us for the time being assume that there are only 4 notes. So, say this is sa, this is re, this is ga, and this is ma. So, a random composition would be a random string out of it, and that you could obtain by doing a random walk on the click. If I join all of them, you could go from sa to re, re to ga, but that is not the case. If you look at Indian classical music, it is true also for Western music, there is a structure. So, in Indian classical music, the raga structure, what it says is, you know, for a particular rag, you can go from sa to re, re to ma, maybe, but not from re to ga. On the other end, you could come from this to this, this to this, and this to this, and there are probabilities associated with them. So, it is not that all edges are with equal probability, you go from sa to re. So, here it will be definitely 1. So, when you go to ma to sa or ma to ga, it might be different probabilities. So, when you do a random walk on this network, actually you get musical compositions. So, are they good musical compositions? And we did some experiments with ragas, and we found that for certain ragas, the random walk compositions are as good as human compositions. We asked people to judge human people, to listen and give ratings to them, and they performed as good as, you know, human compositions. So, random walk is really, you know, a very powerful method, although it seems very simple. Okay, that's a good question. I would definitely be interested in talking in detail about it, but not here. For the timing, I will just say that those were handcrafted. So, there is a musician who knew the basic structure and who gave the probabilities, but you could also learn the probabilities if you have enough musical pieces. So, that is what we always do in case of language. So, when you do a say part of speech tagging, so what happens is a sequence of a sentence is a sequence of part of speech, say noun followed by verb followed by adjective, noun, verb, and so on. So, this sequence can be also looked as a random walk on a particular kind of graph, that is what can come after what and so on. So, you impose a structure like this. A noun can come after adjective, but an adjective has to be followed by a noun, and this kind of rules you could encode in this kind of a graph. You could learn those probabilities, and doing a random walk on these graphs, you could generate valid sentences. So, this is a very standard method, and random walk has a tremendous application in natural language processing.
So, if we assign probabilities ourselves, then is it a random walk?
Yeah. So, as long as the graph is considered, what you are doing by assigning the probabilities yourself, basically it is a weighted graph. When we say we are assigning the probabilities, we are assigning weights to the edges. So, we are defining the graph. So, it is a weighted graph and not an unweighted graph, but then you normalize, you add the weights and divide each of them, divide each of the rows, each of the entries to get the corresponding Markovian matrix, the probability matrix, and then you do the random walk on that. So, think it in that way, that what you are giving are the weights on the edges rather than probabilities, and you compute the probabilities. But the basic assumption of random walk, that you are on a node and randomly choose, this randomness depends on the weights, of course, another node and go to the next node and so on, this is valid, right. So, the strings that are generated are by random walk on this weighted graph. Not any probabilistic model, certain kind of probabilistic model, and these are called Markov models. So, there is a certain kind of probabilistic model where the history, it does not depend on the history. So, what happens is, say in this particular case of musical composition. So, if a node is at SA at say a random walker is at this particular node SA, it will be in the next step in Ray, because this is the only place it can go to in this particular hypothetical example. Now, it does not matter whether it was previously in Ma, or suppose there is an edge here, it was in Ka. So, the history does not matter. So, it is only the immediate past that controls where the particular random walker will go in the next step. So, such processes which does not remember, does not have a memory, it is called memoryless processes or historyless processes. These are called Markov processes. And this particular random walks that you get, that is, you know, the string of nodes one after the another name for it is also a Markov chain. So, this particular chain is called a Markov chain. In particular, to be more specific, a random walk on a directed graph is a Markov chain. Now, undirected graphs are also types of directed graphs where you have edges on both the sides. So, you can generalize it, but to be more specific, Markov chain is defined only for means directed graph, the basic concept. Now, when we talk of Markov chain, we come up with a different set of notions or notations also. What I mean to say is, in the case of graphs we talked of nodes and edges, here we will talk of distributions, probability distributions, because it is a probabilistic process. So, what are these distributions? The first distribution that is important is called P0, the initial distribution. How do you choose the first node? So, one possibility is somebody gives it to you, as we earlier thought, like somebody said that you are at node A and do the random walk. But that is not always very practical, or it is not always very applicable in real situation. In real situation, the initial node usually comes from a probability distribution. It could be A as well as B with some probability, as well as C with some other probability, and so on. So, this distribution is called P naught. This is just a notation, and then the matrix that you have here is called the transition matrix. So, remember, the matrix A was the adjacency matrix, right, for the graph. So, it could be something like this. So, this is the adjacency matrix of any three node graph. This particular matrix D is the out degree, a diagonal matrix which has out degrees in the diagonal. So, what is the out degree of the first column? First row, it is 2, the second one is 1, the third one is also 2, rest all are 0. So, this is D. Okay. And what is then D inverse? Tell me. Actually, the D inverse is very easy to compute for diagonal matrices. It is only 1 by the diagonal entries. You replace the diagonal entries by 1 by the same, the reciprocals. Now, you do D inverse A, and what do you get? So, what are these entries? Is it right? Just check. No, I am doing D inverse A. Check if
the matrix half one half, the diagonal matrix will come on this side, on the left side of the product.
oh sorry, I did this part wrong, sorry, very sorry. Yeah, this is the diagonal matrix, it is coming here. So, after doing this multiplication, check if this is what you get. Okay. So, you get this. So, this is nothing but the transition matrix, which is we will represent it as M. So, here are two very short questions. So, when does M exist? All diagonal elements are non-zero, and that would imply connected, and each node has at least one outgoing edge sort of. And when is M symmetric? So, for undirected graphs, A is symmetric. So, if A is symmetric, is it necessarily the case that M is also symmetric? Let us see. So, this is a symmetric matrix. What will be its elements? If A is this, what will be M? This is, this is, this is, this is. So, is it symmetric? Not, right? So, if A is symmetric, it does not guarantee that M will also be symmetric. There will be, there is a special case where A is symmetric plus there should be some other condition only when M is symmetric. Can you guess that condition? Right. So, all nodes have the same, should have the same degree. So, it is called a regular graph. By definition, a regular graph, for a regular graph, all nodes have same degree. In this case, it should have same out degree, but you already said A is undirected, A is symmetric, that means it is an undirected graph. So, out degree is equal to in degree. So, it is a d-regular graph. So, if all the degrees are d, then M will be symmetric, but in general M need not be symmetric. Also, M has another interesting property, you already know it. M is a stochastic matrix, it is a row stochastic matrix. So, you could now easily guess what are the eigenvalue, first eigenvalue of M and all these different interesting properties about Markov matrices or stochastic matrices. And how do you define the random walk? Again, you have already looked at this. Some of these are repetition, but with more details and some more different symbols. So, you compute the probability distribution of a particular random walker to be. So, let me define more clearly what is P0. P0 is nothing but P01, P02 and so on. It is a vector, where P01 is the probability that the particular at step 0 the random walker is at node 1. This is the probability that random walker is node 2 and so on. So, Pt is nothing but the probability that at a particular point of after t steps the random walker is at point 1 or point 2 and sorry node 1 and node 2 and so on. Okay. So, how we can write Pt1 in Pt plus 1 in terms of Pt? So, it is very clear, you multiply by the random the transition matrix, the transpose of the transition matrix, the Markov matrix we just derived with the previous distribution. So, do I need to explain this also, because we already have derived it in the last class. So, I am not going into the details of this. So, we can represent it in this way. So, you could continue the recursion and ultimately write Pt in terms of P0. So, you multiply the transpose of M t times, that is M transpose to power t, and multiply it by P0 to get Pt. Yes. Y transpose. Okay, let us see. So, M is the out degree, right, normalized by the out degrees, and so this is half, and say this is 1. So, I give you a distribution that at this point of stage with probability A you are here, with probability B you are here, and with probability C you are here. So, this is the vector which I call PT, right, by definition this is what is PT. Now what will be PT plus 1? What's the probability is that in the next step you will be at B, you could come to B from A, so it will be half into A and that is all, right, for B. So you see when you compute this, you do not look at where you can go from B, you look at from where you could have come from. So you could come from A. So in case of C, what would be PT plus 1 C? It will be B into 1 plus A into half. So you see 1 and half is if you do the transpose of this particular matrix, actually I am not sure these two are not the same, so that is why. So if you do the transpose of the M matrix, then only you could get this, because the rows of A will be actually half and half, but you are not multiplying by half and half. So if you do M and PT, you would have been actually multiplying A into half and B into half and so on, which is not the case. Where you are going to, you are looking at from where you are coming. So that is why you do the transpose and then multiply, because that will give you the from where you are coming, the rows will become those particular entries. Okay. So few more properties of Markov chains. One is Markov chains are symmetric, could be symmetric, not necessarily symmetric. So what symmetry means is the probability of going from U to V should be same for that of going from V to U for all node pairs U and V. And when does it hold? It holds for undirected regular graphs. So for undirected regular graphs it is symmetric. And the good point of doing a random walk on a symmetric graph is if you have a random walk sequence V0 to Vt, when you reverse it, that is Vt, Vt minus 1, if you consider that random walk, both have the same probability if V0 and Vt are same. But this is not a very useful concept, because this is a very restricted class of graphs for which it holds. What usually is more interesting is called time reversibility. So if the reversed walk is also a random walk, then it is called, for every random walk on the graph, if the reversed walk is also a valid random walk, need not be with same probability, then it is called time reversibility, a Markov chain with time reversibility. So for which kind of graph this will be true? Any undirected graph this will be true. Even if it is not regular, if you could go from A to B, then definitely you can go from B to A for any undirected graph. So for any undirected graph is time reversible, but directed graphs also could be time reversible under certain specific cases. And there is a stationary or steady state distribution, it is called P star, for which this particular thing holds, that is P star is M transpose star P star multiplied by P star. What it means is, if your probability distribution is P star for being at any node in the random walk, then it will remain so forever, because remember the recursive equation which is M transpose. So remember this is the equation, recursive equation. So if you replace it by P star and this also by P star, then you remain on that particular distribution forever, no matter your t goes to infinity, you are in the same place. So these steady state distributions or stationary distributions are very interesting to study for any graph. And again, you know a lot about stationary distributions.
How can a graph that is not undirected be time reversible?
You have to have cycles.
No, it can be. So what I mean by undirected is actually you have, say this case, say this has weight W1, this is W2, this is W3. Okay. There could be a directed graph like this. So I don't consider it as an undirected graph because the weights are different. This is the special case I was talking about. since the weights are not exactly same, I can't represent it as an undirected graph, a corresponding undirected graph. So, it is a directed graph, but still for this also you will have the random walk time, which will be time reversible. So let us prove some properties about stationary distributions. The first one is again very easy to prove. So, for any graph, the stationary distribution P star, so for any node, if you calculate P star V, V is the node, it is the degree of V by 2m, where m is the number of edges in the graph. Can you show that? Think for a while. I have to show that this holds, right? P star, sorry. This is what I need to show.
Is this a property of P star or of M?
It's a property of P star. For any m, this holds. That is what you have to prove.
So that means even if you continue multiplying with MT, you don't have any.
Right. So this is the equation. What I am saying is this particular condition satisfies this particular equation, this particular instantiation of P star. Say degree of V by m. These are all degrees by m, 2m, sorry. And here what you have is it's the transpose of m. So basically this will be degree of 1, this will be degree of 2, and this is what was original Aij with Ji, it is transpose, so original Ji, so it will be A11, it will be A12 and so on, sorry 21. So A is this matrix, the adjacency matrix, got the point? And so on. So this will be your A12 by D1 and so on. So this will be, now you multiply it by this particular vector, which is nothing but D1 by 2m, D2 by 2n, and can you see what happens? D1 gets cancelled with D1 when you multiply the first thing, and you get A11 by 2m plus A12, sorry A21, not A12, A31 by 2m and so on. And what happens when you add A11, A21, A31 and all? It is degree of, which is nothing but this, okay, again the same thing. So could you see that this happens, but this happens only for what kind of graph? This happens only for undirected graph. So I am assuming that sum of A11, A21 plus A31 is same as sum of A11, A12, A. So the out degree and in degrees are same. If this holds, then this particular thing holds. Okay, and the second question is why we are dividing by 2m? Sum of the degrees is twice the number of nodes, twice the number of edges. And again a very easy question, for which type of graph the uniform distribution is stationary? So the probability of being at any node will be same for a regular graph. And the stationary distribution is unique. I am not going to prove it, we already proved it using eigenvectors and things like that previously, right? But when? Do you remember? When will be the stationary distribution unique? When the graph is connected. So let us see why. So suppose the graph is disconnected and it is like this. So depending on what I initialize, what is my P0, my stationary distribution will change. If my P0 was half, half and 0, the stationary distribution remains at half, half and 0. And if my P0 was 0, 0 and 1, my stationary distribution remains at 0, 0 and 1 and so on. Rather let me do it half, half. So, what was my initial condition P0? Based on that my stationary distribution changes for a disconnected graph, whereas for a connected graph, no matter what P0 you start with, your stationary distribution is unique and remains always the same. And as t tends to infinity, you keep on doing random walk for large number of steps, the stationary distribution that you arrive at will converge to P star. This also we saw. What it essentially means is mt power t, no matter what you multiply, which vector you multiply here, will converge to P star, right, as t tends to infinity. So, you keep on multiplying, it is the power iteration method, it will converge. You keep on multiplying the transpose of the transition matrix again and again and again, and it will converge. How fast it converges is another story, we will look into it. But the question is, for what kind of graph it won't converge? Can you think of it? As I said, for disconnected graph it will converge. It is a different matter that it won't be unique, it will depend on P0, but it will converge to something. For different initializations it will converge to different points. But the point I am asking is, for what kind of graphs it won't converge? Can you speak a little louder? Clicks it will converge, actually clicks it will converge very fast. What it will not converge for is bipartite graphs. There is a very interesting thing about bipartite graphs. Let me just tell you a little bit more about them. Think of an undirected bipartite graph like this. Suppose your initial distribution was such that you started from a node in this partition. Then in every even iteration you will be in a node from this partition, right? T equal to 2, t equal to 4, you will be, and for every iteration, odd iteration, you will be in this partition. So, what happens, even if it goes to infinity, for every odd step, all the nodes in this partition will get some non-zero, probability distribution, stationary distribution, whereas this part all of them will get 0, and the reverse will happen in the even steps. So, it will not converge, but it will oscillate between two distributions. So, this is a very special case, and that is why bipartite graphs are needs a special treatment. We will look at them in the Friday lectures, actually more about them. And a few more points about time reversibility. So, if P star I is the stationary distribution, then what time reversibility means is, suppose you are in this node, consider this particular case, this is node I, this is node j. So, the probability of you being here in a steady state condition is P star I, and you being here is P star j. So, what is the probability of traversing this edge from this to this direction? So, it is Mij, right, and what is the probability of traversing from this direction if you are here? So, it is Mji. So, what happens is, what is the probability that you cross this edge ever? It is P star I into Mij. You could either come from this direction or P star I into Mji, right, and sum of these two actually. P star j into Mji. So, sum of this, you could either traverse it from this direction or traverse it from this direction, and it turns out that actually both of them are same, because remember what is P star I for a undirected graph? It is di by 2m, and what is Mij? Since the edge exists, it is 1 by degree of I, right. Since the edge exists, the adjacency matrix has a value 1 for Aij or Aji, but the Markovian matrix we have divided them by the degrees, so it will be di. So, this cancels out and you will have 2m, sorry, into Mij. P star I into Mij will be this, and same holds for this. So, essentially this is true. So, this is a property of undirected graph, and as I said, undirected graphs are time reversible. So, another way to state time reversibility is this particular condition. So, this has a very interesting connotation. We move along every edge of a graph from any direction with the same frequency. So, this 1 by 2m, take any edge of the graph, the probability will come as 1 by 2m, right? Got the point? So, I have not assumed anything else, that this edge has this property or that property. I have taken any edge and it comes as 1 by 2m. And there are, I have to add these two probabilities. So, both are 1 by 2m. So, I will add them. So, 1 by 2m plus 1 by 2m is what? 1 by m. So, 1 by m is the probability that any edge is traversed. So, in a connected graph, the probability of traversal of any edge in the steady state condition is always 1 by m. So, therefore, the expected time in which you will come back to the same edge again, number of steps in which you will come back to the same edge again is m, inverse of the same. So, I already told you this. You could also compute the expected number of steps that you need before revisiting a node. Suppose you visited a node now, after what is the expected number of steps after which again you will revisit this node? And that depends, no, it is not 1 by n, that depends on the degree of the node actually. So, it is the degree, it is a function of the degree of the node, and then, so do it as an assignment. It's easy, you can easily do it. Okay, and just before we finish, let's see some more interesting some more important parameters of random walk. In tomorrow's lecture, we will connect them. So, in today's lecture, I am just giving you some properties, the mathematical properties. Tomorrow's lecture will show how these can be used in developing practical algorithms. So, one important concept is that of access time or heating time. It is called Hij. So, suppose you are at node I now, what is the expected time when you will hit node j? It is called Hij. I am not telling you how to compute it, I am just giving you the concept. So, what is the expected number of steps in which you will reach the node j? And commute time is, you are currently at I, what is the expected number of steps in which you will go to j and then you will come back to I. And clearly that commute time is sum of Hij plus Hji, right. Now, can you relate commute time and access time to something interesting that you know, say in P2P networks, right. So, suppose you are asking for, looking for something which is sitting at node j and you are doing random walk for searching it, then the expected time when you will know that this thing exists, basically your random walker will know, is Hij, and the commute time is by the time you will get the search result. So, it will come back to you again. So, that is so these are I am just giving you some pointers on why these are important. And another thing is cover time. So, starting from any particular node or any particular distribution P0, what is the expected number of steps in which you will reach every node? That is what is called commute time, cover time. And why cover time is important? Again, searching, right. If your graph has a very low cover time, it is very easy to search, it is very fast, searching will be very fast. But if it is a very high cover time, random walk may not be a good method to search for something on the graph, because there might be one node sitting in some corner which you will never reach, no longer how long you do it. But mind you, we always assume that the graph is connected, so nobody is cheating. It is not that the graph is disconnected, then you have more problems. So, before we end up, we have some problems. So, what is the access time for any pair of nodes for a click with n nodes? No. Say I am in this node and I want to know the expected time of reaching this particular node, right. 1 means you are always assuming that I will in the first step go here, but I could go here, 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 go around, 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 and after say 1000 iterations come here. I can do that, right? So 1 is not the answer. So how do you compute it? Let's see. So for any click, what happens? What are the weights on probabilities on the edges? 1 by n minus 1. Every edge connects to n minus 1 other nodes. So this is 1 by n minus 1. So the probability, say I am looking at u and v. The probability that u goes to v in one step is 1 by n minus 1. So it goes in one step. What's the probability that it goes in two step? So first step it goes to some random node, which is with probability n minus 2 by n minus 1, and in the next step it goes to this node, and this is the case for 2. I am finding the expected value, so I am multiplying it, and you go on in this way. So can you generalize? It will be right, and t goes from. So this is the access time. So very simple looking problems aren't always simple. So that's why actually access time and cover time and commute time, these are usually very involved computation for any graph. And if you kind of simplify this, actually it comes as n minus 1. So intuitively what it means is there are n minus 1 nodes. If you go n minus 1 times, you will reach this, you expect that you will reach it at least once. So that's the intuitive understanding. So, and can you express the cover time of a path by access time? So path graph, you know. So this is suppose a path. So this is u, this is u0, u1, u2, u5, 4. So can you, what's the cover time, worst case cover time for this? Can you express it as some sort of access time? So what's cover time? You have to cover all the nodes. Suppose I am saying your starting node is u0, then you have to cover all the nodes, right? So that's your cover time. Can you express it for paths? Actually you can express it as access time. So h 0 4, you get it? So if you can go to 4, if you can access 4 from 0, you have to essentially access everything which is in between 0 and 4, right? Since it's a path, you can't go to v3, you can't go to v4 without going to v3 and so on. So if you ensure that you have gone to 4, you ensure that you have reached every node. So for a path, the cover time is equal to the access time of the first and between the first and the last node. And for which kind of graphs cover time is infinity? Disconnected graphs. So simple. And what can you infer about a graph which has a large number of nodes but very low cover time? It can be a click, yeah. So it might be a small walled sort of graph. So okay, we will stop here, and tomorrow we will see how this can be applied in some practical algorithms. Especially we will look at information retrieval algorithms. We have already looked at page ranking. We will look at 2 other algorithms which use some modified forms of random walks, because PageRank has certain problems. We will see what are those problems, and then we will go to that.